right, we are moving into our last section of Chapter 2 on the precise definition of limits. This is section 2.7. And so some of the terms that we saw in the preliminary definition of a limit in the first section were really vague. So in this section, we are going to give limits a solid mathematical foundation by transforming this definition into something that's a bit more precise. So, for the previous definition of a limit, what we said was assume that the function f is defined for every x value near a except possibly at a itself. And we want to recall that the limit as x approaches a of f of x equals L means that f of x is arbitrarily close to some number L for all x values that are sufficiently close but not equal to a. So, this sufficiently close and arbitrarily close is what we're going to bring down into a bit more precise definition. So, in order to make this more precise, we must use distances between these values. So let me remind you about the distance between, say, 2 points. Call it A and B. Then the distance is equal to the absolute value of A minus B or the absolute value of B minus A. So when we bring things down to be a little bit more precise, then we're going to need an absolute value. So if I ask you what's the distance between f of x and f of L, and knowing that with our absolute value, we could write absolute value of f of x minus L. We could also, to define the distance between x and a, we could do the absolute value of x minus a. So these are going to be used in our more precise definitions. So, since both of these are supposed to be arbitrarily and sufficiently small, then we make use of two Greek letters. One is epsilon, and the other is delta. So this is epsilon, and this is delta. So it's the lowercase e and the lowercase d of those. So we make use of the two Greek letters epsilon and delta to bound our distances above. So epsilon is going to be seen as a y value and delta is going to be seen as an x value. So here's kind of what we're going to do. For any epsilon greater than 0, there exists a delta greater than 0 such that, so basically I'm just defining that I have a small number that's bigger than 0 positive and I have another small number that is also bigger than 0 such that the absolute value of f of x minus L is less than epsilon whenever 0 is less than absolute value of x minus a, which is less than delta. And so, basically the difference between the function value and the limit that is going to has to be really small, and the distance from x to a has to be really small as well. So now, let's determine some exact deltas given a specific epsilon. So, if we move on to the next page, then we have a graph here of f of x. We don't know exactly what the function is. We just have the graph of it. We could define what the function is. It is linear with a hole in it, so we would have to do some undefined rational function there at x equaling 3. But we are looking at the limit around 3 is defined. It is equal to 5. So notice here from the left we're going to 5, from the right we're going to 5. But we need to, for each value of epsilon that's given, determine a delta that's greater than 0 that satisfies each of these. Now those distances, we're going to kind of make some rectangles here and kind of determine where that has to be. So this delta, if we go back to some idea of absolute values, this in an absolute value inequality is kind of giving us a distance from A. Okay, now A is our 3 here. Okay, so we're going to kind of look to the right and to the left of A what our delta is going to be in order to satisfy, in this case, that our epsilon is equal to 1. Now, so the distance between f of x and L, well, where is f of x? f of x, here's our limit, okay, L, and f of x, if I enter this in here, so the absolute value of f of x, which is changing, minus our limit value has to be less than 1. So that means if I have some function value that's less than 1, with distance of this limit, then that means I could go above 5 by 1, I could go below 5 by 1, and still hold true with this inequality, okay? Actually, why don't I exchange that L for a 5, since that's what it's actually equal to. Minus 5. So f of x minus 5 is less than 1. So I'm going to say, okay, go 1 above 5 and 1 below 5. Okay, so I'm kind of making this rectangle here. Within this region, I'm going to be able to determine delta. Now that delta is going to be determined by finding where the function value is on each one of these lines. Okay, so across my function value here and here. Now I'm going to correspond that down on the x-axis. Okay, so basically we're kind of defining this value or this rectangle right here. Now to find our delta, we have to determine the distances that I have here from 3. So this distance around L was our 1 for our epsilon. We need to know what is the distance from here to here after I've created from that restriction. I have to be less than 1 from our distance of L. Then from our points on our function, we drop them down into our x's. I now create a distance from 1 to 3 and from 3 to 5. So here, what are these distances? From 3 to 5 is 2. From 3 to 1 is 2. Therefore, I'm going to define delta to equal 2. Delta has to equal 2 here. I have to be within 2 of my x value of 3 so that my function value has to be within 1 of my limit value. Okay? All right. Now, if you hopefully maybe if you're with a pencil, you can erase what you just did there because now we're going to have a different problem where I'm going to restrict my f of x to be within my limit value of 1/2. So here I have an epsilon of 1/2. So again, trying to figure out if I'm a half away from 5, here's my limit. If I'm a half away of 5, I'm here. Half away is here. So I'm going to go across to my function. You can go all the way across if you want. But what is important is us to designate where we are intersecting on that function. So I'm here and here. Now, I'm going to drop down to my x-axis and I'm going to determine how far away from my a value of 3 am I allowed to be. Well, here's a distance to the right. Here's a distance to the left. Notice that's at 4 and at 2, which are distances of 1. If we let delta equal 1, then we are within restriction. Again, now I've created kind of this rectangle here that we are honing in on. And hopefully you see is that epsilon gets smaller and smaller and smaller, that this rectangle gets smaller and smaller and smaller around that limit, and hence there's the precision of that definition of a limit. Okay, so those are some tangible things to find delta. Here is where we're going to define the limit. And so, by definition of a limit, assume f of x is defined for all x in some open interval containing a, except possibly at a itself. So this is going to look similar to our preliminary one, but we're going to clean it up now by using our distances here. So the limit as x approaches a of f of x equals L means that for any epsilon greater than 0, there exists a delta greater than 0, such that the absolute value of f of x minus L is less than epsilon whenever 0 is less than x absolute value of x minus a, which is less than delta. And that right there gives us our formal definition for a limit. And we're going to use that in order to prove that the limit exists. So this is a little bit more abstract than just kind of some tangible stuff, but it's important for us to see that. So here's some steps in doing what we call a delta-epsilon proof. We want to find delta by using our function and our limit inequality to algebraically make this look like the inequality with x minus a. So basically, we're going to cheat here, okay? This is our cheat step. And we're going to look at f of x minus L less than epsilon to make it look like the absolute value of x minus a, using some algebra techniques. And then, to do your proof, this is what I want you to start with. We're going to say let epsilon greater than 0 be given, and delta equals something in terms of epsilon, okay? So I'm going to say delta equals some number, okay? It's going to be in terms of epsilon. You're going to have an epsilon in here. Such that if 0 is less than x minus a, which is less than delta, that's going to be my start. Then we're going to use algebra at that point to finish at the very end with this inequality. And I'm going to show this to you with a linear one. I'm not going to go too deep into this. We can actually do that with some quadratics, but I'm not going to get that into that depth, okay? So here we go. We're going to use the precise definition to prove the following limit. Specify a relationship between epsilon and delta that guarantees that our limit exists. So here we go. Here's our cheat step. We are going to start with the absolute value of f of x minus L to be less than epsilon. And I'm going to plug these things in. So here, in my limit, what do I have? Well, this is a, this is my function, and this is my L. Okay? So I'm going to plug f of x to be 4x minus 2 in there, minus the limit, which is 10, which is less than epsilon. Now, what I need to do is use some algebra to take this down into the x minus a absolute value. Well, what's a? I need to get an x minus 3 inside there, okay? So I'm going to use some algebra. I'm going to combine. That parenthesis actually doesn't make a difference, so I'm just going to drop it. I'm also then going to combine like terms, so I get a negative 12 less than epsilon. Because I have an absolute value, I can take this 4 out. That is common. Now I can factor it on the inside, but I can also take it on the outside. And when I factor it, I get an x minus 3 on the inside, which is good because I need that 3 to be for my a. And then I'm going to get the absolute value of x minus 3 by itself by dividing by 4 and dividing by 4. So I get x minus 3 is less than epsilon over 4. Now, remember, this is x minus a. And what do we group with that x value? We group delta. So right here is the definition that I want to make for delta. I want delta to equal that epsilon over 4. Okay? So basically, you kind of have your proof, except for now we have to start here and work ourselves back. Okay? So we do this, a nice slick way to be able to cheat, quote unquote. And then we're going to now write our proof, okay? So go back, I'm going to scroll back up here to get this little step right here. I want you to say, let epsilon be given and delta to equal, in our case, epsilon over 4. So we're going to say, let epsilon greater than 0 be given and delta equal epsilon over 4. Of course, there's a delay, sorry. Such that if, and we're going to start with that inequality, so such that if 0 is less than the absolute value of x minus, in this case, what is our a value? Our a value back in our limit is right up here. So I'm going to go ahead and write x minus 3 is less than delta. Then, now here's kind of the thing. You can keep the combined inequality, but here this is just basically symbolizing that delta is greater than 0, that this is all positive. So at that time, normally I just drop this part and say, okay, then x minus 3 is less than. Here's where I'm going to take what I let delta equal and sub it in. Less than epsilon over 4. And in a proof, you don't necessarily show your work. So we're just going to kind of go step by step here. We are now basically going to start here and go backwards, okay? So I need to now multiply 4 on this side. So I get absolute 4 times absolute value of x minus 3 is less than epsilon. Then I'm going to distribute that back in and get 4x minus 12 is less than epsilon. So I'm right here at this step over here in my cheat step. Then I need to bring it back to where I can recognize that function. And if you want to, you can kind of bring it back up into here and say, okay, well, that's equal to 4x minus 2. And then I could also then do minus 10, which is less than epsilon. And right there, I have my function value, my limit value. Therefore, f of x minus L is less than epsilon. And that right there is a delta epsilon proof that sometimes a lot of students kind of have a hard time with, but it should be pretty basic. Again, it's kind of formalizing the idea of getting smaller and smaller and smaller, closer and closer and closer to that limit value within those ranges according to that precise definition. Okay? So there's actually not many problems that I'm asking you to do out of section 2.7. Just make sure that you're able to do something like this on a test. That is probably going to be something that's not prevalent, but you probably would have at least one problem on a test like this. So this concludes chapter 2. We will then move into chapter 3, which is our moving into derivatives, which is a huge section of Calc 1. And so we will see you on the next time. Bye-bye.